grades were a little bit lower than I'd hoped, and also I noticed there were a lot of hypergeometric random variable problems. And so I ended up scaling the grades. When you look at the grade book, you'll notice that there's this the easiest way for me to do it, instead of changing everyone's grade individually so that it was equitable, was to, you'll see, it's insert. Basically, if you want to know what your grade is, take whatever grade you have and take half the difference between you and 100. And that's so, like if you have a 90, you actually have a 95 in the grade book. If you have an 80, you have a 90. That sort of thing. So if you have a 50, you would have a 75. So it's not as bleak for some of you as you might think when you first look at that paper, if it makes you feel better. But I do want to take a look at some of these because, like I said, there were a lot of hypergeometric random variables, and yet there were, I mean, it should have been, some of these were relatively easy, I think. Everyone got number 1 right. Good job. Number 2, I don't care if you got it right or wrong. I can't remember if anyone got it wrong. If you really want me to, we can look at it later. But let's just blow through these because they're going to come back to haunt us later. So there's a few. We're not going to do every single one of these, but there are some that I want to make sure we remember. So the Euclid deck, this is the first of the many hypergeometric random variables. And I guess it puzzles me. I'm not sure, even before we knew this was called hypergeometric, we were doing problems like this, and you were doing them correctly. And now that we name it, it's like, oh, now we can't do it. Or maybe you just want to make it into a binomial random variable. There were a lot of people, not a lot, but a number of you took some of the hypergeometric random variables and interpreted them as if they were binomial. But this one, totally hypergeometric. So you have 6 choose. How many do we want? I choose 5, exactly 2 of them. So So you want 2 of them to be hearts. You're choosing 2 out of the 6, and out of the other, 18? You're going to choose an additional 3 cards. So it's basically you're playing euchre, and you're going to get 2 hearts and 3 non-hearts. And this is out of 24, choose 5 is the idea. So it's that simple. Don't make it out to be more complicated than it needs to be. And if you don't like knowing the name hypergeometric, don't think about it. Just think, okay, we've done this before so many times. You can do this. It's an easy problem. And same with some of the other ones. This one as well, relatively simple. So this one is conditional. Once you see no, you know something, it's conditional. You can do it one of 2 ways. I'm going to do it this way with the number. The number of ways of having 3 red, all over the number of ways of having 3 the same. So this is just the way I'm going to do it, but you could have done it something similar. Now, despite the fact that this is a conditional probability, this is related to the hypergeometric random variable. So you could have done this using the probability of 3 red, which would be a hypergeometric random variable probability, and then the probability of getting 3 the same. Once again, hypergeometric. So that's why I said it kept coming back, and if you didn't know your hypergeometric random variable, you blew the whole test. So that's why I feel bad about the fact that there was so much hypergeometric. But anyway, number of ways of having 3 red, you're just choosing 3 out of 5. So you got 5 red balls in there, and you're choosing 3 of them. And then on the bottom, if you want 3 the same, to get 3 the same, either they're all going to be red or they're all going to be white. So we'll just put the reds plus the whites. So there's this many ways of getting 3 reds, and this many ways of getting 3 whites. I forget what that fraction reduces to, but a number of you got this right. You did a good job. I mean, on the whole, grades were a little lower than I'd hoped. So I was trying to decide, how do I deal with this? And if I let you do corrections, then that makes more work for me, to be honest. So that's why I decided to just scale everyone's grade up for now. And then you'll do better on the next exam, I'm sure. And I thought we'll go over this to make sure that you see what you did wrong. Okay, so this one, I think I spoke with someone and said, oh, there isn't any Bayes theorem. Whoops, this one's a Bayes theorem problem. So just to remind you, it is a conditional probability. So, you're just dealing with conditional probability again. So you're here, you either have mathitis or you don't. So here I'll do this mathitis. I don't know what mathitis really is. You either have it or you don't have it. And then if you have it, then you either test positive or negative. Same thing here, positive or negative. So mathitis, it says that 35% of the entire population suffers from this disease. So 35%, 65% are down here. And then if you have mathitis, let's see, positive, okay, positive. So if you have mathitis, it looks like there's a 14% chance that you'll test negative for mathitis, and a 99% chance you'll test negative for mathitis if you don't have the disease. And then this is just we're just going to multiply these out. I'm not going to do the calculation, but it's what is the probability that you suffer? Okay, so this is 35 times 0.14 all over 0.35 times 0.14 plus 0.65 times 0.99. Did I start this recording? I did. Sorry, I just want to make sure. So yeah, that's the general structure of Bayes' theorem, but you could get it without knowing Bayes' theorem because you all know how to deal with tree diagrams like this, and you know conditional probability. It's just that it's probably, the day before break, you're thinking about going home and doing whatever it is that you do. And so, timing, it might have been better to do it on Wednesday actually than on Friday, in all honesty, but it is what it is. Maybe I'll do better next time. Okay, so that was 5. Oh yeah, so we move over here to 6. Is this, oh yeah, so yeah, it's just more hypergeometric. Like I said, when I made up the key to this, I just realized, oh, so much hypergeometric. So anyway, this is also hypergeometric. So, I mean, it doesn't look like it, but it is. So here, let's just illustrate. I won't do this one completely. You all know how to do expected value. You were floundering around, those of you who got this wrong. You got something that looked like an expected value, you just had the wrong probabilities, that's all. So, but here's how I might set this up. I would have the x is the payout, the probability, and then you know the deal. You do xp to get the expected value. The sum down here, this will be the expected value. And then you'll do x squared and x squared p, and we'll add these up to get the expected value of x squared. And then you have to remember the variance formula. Or, oh, wait. Yeah, variance is down here. I knew it was there somewhere. But here, let's get the probabilities. I think you can all handle the rest of the chart. So there's 2 things that could happen. Oh, no, there's 4 things that could happen. Yeah, that's the thing. And yeah, like I said, I realized that it's just so complicated. So you either lose $3, and that's if you get no spades. So the probability of getting no spades is 39 choose 3 over 52 choose 3. Oh, I need to say something about this problem. I just realized when we get done, because there was an alternative way to interpret this. And so I realized that. So I'll have to make sure that I've caught all of the alternative people. There was a second way to think of this. Okay, so there's -3. You can do the rest of this. You could win $2, and you win $2 if you draw exactly 1 spade. So 13 choose 1, 39 choose 2. Yeah, you start seeing the pattern. You're like, oh yeah, this is the way it's going to be. And then you win $4. If it's 13 choose 2, you get 2 spades, 1 other card. And this is out of 52 choose 3. And then $6 if all 3 of them are spades. 52 choose 3. So that's the structure of the table. And you can go through this. Now, I will say this, that it was not entirely clear. So I want to make sure I gave everyone credit where credit was due. So you'll have to let me know afterwards if you're in this boat, because I discovered some of you, or at least 1 or 2 of you, interpreted this as being, here, let me demonstrate. It's easier to demo. With replacement. So here's the difference. Here's how I was imagining that you play this game. So you've got your cards. Why did I do that? I don't know. You've got your cards. You draw 3. Here's your 3. 1, 2, 3. So you've got your 3 cards, and then we pay you based on these 3 cards. So no spades, I lose. Okay. So that's the way I was interpreting it. Some of you interpreted it this way. So here, check this out. We shuffle, we cut. Here's your first card. Is it a spade? Oh, it is. And then we put that back in there, shuffle, and cut. Here's the second one, not a spade. So we've got 1 spade. So you see how this is working? And then the third one, not a spade. So there, that person won $2. So if you did it that way, then this is actually a binomial random variable. So if you interpreted this as the way that I just demonstrated, I should have at least acknowledged it somehow and given you credit for doing it, even if you didn't get the right. I forget what the right answer is in that case. But anyway, if there's a question as to whether or not you did it right, or if you thought of it as a binomial random variable with replacement, see me afterwards. I'll give you credit. If I didn't notice it before. If I noticed it, like you might have done the probabilities correctly, but then you blew this part. I don't know. So you might still deserve to lose points. But there's that. Okay. So you know the rest of this. I'm not going to go through that. Unless, well, here, let's just, let's see. You can stop me at any time. So if you don't like any of this, let me know. But if you have the whole binomial version of this, then come see me afterwards, and I'll make sure, if you think that I didn't give you credit. Okay, let's move on. Yeah, stop me if you have a question. Let's see, this one, probability mass function. This is just a straightforward binomial random variable. The probability function is just the probabilities. You could either do it as a table of probabilities or as a function. And I think, what is this, 4 times? You're rolling a die 4 times, number of ones. Okay, so you have 4, choose x. This is the function version, but you could have just made a table with 5 entries, 0, 1, 2, 3, 4, for the different outcomes. So then 1/6 to the x and 5/6 to the 4 minus x. So this is where x is any integer between 0 and 4. So you can either do it this way or just make a table with all the different ones. And once again, binomial random variables, we've named them, but we don't have to think of them as being binomial. You could just think of them as, oh yeah, I know how to do this because we've been doing this. Not as much as the hypergeometric. The hypergeometric we've been doing from right from the beginning, I feel. Once you learned about combinations, we started doing. This requires you to know about independence. So, okay, so there's that. I'm going to skip that. You can deal with that yourself. Okay, this one, binomial. So this is totally, wait, is that right? He will make at least 2 of them. Yeah, the probability that x is greater than or equal to 2. Yeah, this is straightforward binomial. 2 plus the probability x equals 3. So that one's straightforward. Yeah, just if you want to know, n is 3, and p, the probability of success, is this. So you just crank that into the binomial formula. What are we on? 18? I guess 19 is next to it. Casino game, coin flip 3 times. Oh yeah, just another expected value invariance. I guess I felt like there was some redundancy when I made out the key. I just kept seeing. So this one's binomial though. So this one, $5 for 3 heads. Otherwise you get nothing. Wait, $1 for 2 heads, $5 for 3. Okay, so here's the table in case you didn't catch it. So we have x and the probability of x. And then, of course, you know the rest. You do xp, and then you do x squared p. Add up these 2 columns, this one and this one. So that's not a big deal. But you're either going to win nothing, you're going to win $1. Wait, where is it? $1, or you win $5. Okay, so let's deal with the $5 first. That's the easiest one because that's if you get all 3 heads. And there's a 1/2 to the 3rd power. Here, I think you could probably do this without, in fact, a couple of you, one of you did this but missed one of you wrote out the sample space. There's 8 things in this, so you had the sample space over here and you just picked out the ones that gave you the prize. But yeah, in fact, let's just do it that way. Here, you can imagine the sample space. There are 8 things. and in exactly one of them, you'll have all three heads. In three of them, heads, heads, tails, heads, tails, heads, tails, heads, heads, those three, you have exactly two heads. And then in all the rest, you have 0 heads. So I suppose this you could do without just doing the probabilities. But heads, heads, tails, heads, tails, heads.
Does order matter?
No, you're flipping coin 3 times. Okay, the other way you could do it is you could use the binomial probability 3 choose 1 times 1/2 to the first times 1/2 to the second. Or, sorry, 3 choose 2, how about? Okay, so 3 choose 2. It's a binomial probability. 3 choose 2 times, this is the number of tails, here's the number of heads. So, yeah, we've been flipping coins since the beginning, haven't we? You did a sample space, 8 things in the sample space of flipping 3 coins. Or flipping coin 3 times. Yeah, order definitely matters. Oh, and we're using combinations here. Yeah, kind of contradictory, isn't it? Well, anyway, so I'll let you do the rest of that yourself. Let's see, this one was just confusing. You know, see, there again, I feel like these were a little bit more complicated than they should have been. So I felt like I should do penance. And the penance that I decided on was not to make you do any more work, but just to scale up the grades a little bit. But anyway, yeah, this one, you see that we're doing make fewer than 3 errors during the next 2 hours. So we need to know how many, let's see, 2 per hour, that's 4 for every 2-hour grading period. So, period. So this one's Poisson, by the way. So you're making, if you think of me as sitting down for 2 hours and grading, then I go for a walk, and then I sit down and grade for 2 hours, and then I go for a walk, and so on. Then for every 2-hour grading period, I should have, on average, 4 errors. That's a lot of errors. I guess I was thinking of, like I go grade for the AP, and we do 2-hour blocks. It's a lot of errors, though. I would hope I wouldn't be making that many. Wow. Someone's angry. But anyway, then fewer, so the probability of fewer than 3 is the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2. And then you just use so just to give you a quick example, this is going to be lambda to the I, or n, or whatever letter you want, e to the negative lambda over n factorial, so 2 factorial. So you'll add these up. I think this just ends up being e to the negative 4, and this ends up being 4e to the negative 4. So add all that up, or just leave it like this. That's safer. It seems like at least one of you made an arithmetic error when you added these up. Okay, moving on. Let's get on, finish this up so we can move on to the next thing. Okay, so we have 5 cards. Oh yeah, another. Once you have cards coming from a deck, hypergeometric. 3 of them are spades. Why? Why did I have so many? I don't know. I think I was pulling from several different tests. And I was like, oh, that looks good. That one looks good. Just put them together. Anyway, yeah, this one's hypergeometric. I'll just write down the answer. It's so, I mean, once you know the structure of the hypergeometric random variable, it's pretty easy. So exactly 3 spades. The other 2 are whatever over 52, choose 5. That's good enough. So here's a string of things dealing with this person that's not me because they spell their name differently. But they're all Bernoulli trials, but then you have to distinguish. So this, hopefully you could have figured out, but free throws, this is geometric. Oh, no, negative binomial, sorry, neg binomial. So because we're looking for 4th basket, so R equals 4. Here, probability of success is 0.75. Oh, expect to shoot. So you can always go back here and find that negative binomial. That's right here, R over P. Attempts 6. Once you have a fixed number of Bernoulli trials, this becomes binomial. So more than 4 means the probability that x equals 5, and the probability x equals 6. So, but it's binomial with n equals 6. So if you didn't get it right, just go back up there, binomial, n equals 6, and hopefully you'll get it. Okay, what do we got here? That's B. Let's do C. Free throws until he misses. Okay, so there, that's geometric, because you're doing something until you succeed, which in this case, success means missing. So you're going to do this over and over again until you miss. And so the probability he shoots more than 2 times, well, that's going to be 1 minus the probability he shoots once, plus the probability that he shoots twice. So remember, what we're saying here is we're going to keep throwing until we miss. And so you could probably even do this without knowing it's geometric, because this is a 25% chance of missing, because this guy's a good free throw shooter. And then 75% chance of making the first one, and 25% chance of missing the second one. So just 1 minus that's the easiest way to do that. Then the last one, repeatedly until you make 10 free throws. Okay, so that's going to be R equals 10, and this is negative binomial. And we want to know the probability that x equals 13. So you can go back up there to that negative binomial and do that probability with the p equals 0.75. All right, one more, and then we'll be done with this for now until you come and beg me for mercy later. Okay, so during the next decade, okay, so here it's another Poisson thing. Lambda is equal to 1 per decade. And so I want to know that what's the probability that we get 2 during the next decade? You might say, why would a hurricane ever hit Mount Vernon? Well, about 12 years ago, we had one come through and destroy a bunch of trees and stuff. Hurricane Ike, I believe it was called. But I remember we ended up buying our generator. So we got one of those, like we went to Home Depot up in Akron because Akron had power, but we didn't. But anyway, so let's see, this is 2 hurricanes. This is the probability that x equals 2 with a lambda of 1. So you can go up to there to the Poisson land and figure that out. And then this last one is a little bit weird because it says, what is the probability that in exactly 6 of the decades during the next century, no hurricanes hit Mount Vernon? That's actually binomial with n equals 10 decades. So a century is 10 decades. And we want to know the probability that x equals 6. The probability of success is no hurricane hits Mount Vernon. So the probability of success is the probability of no hurricane in 1 decade, which is going to be just e to the negative 1. So this, let me just put a little cloud around it, that is Poisson. Yeah, so there I mixed both Poisson and binomial, which was a little bit mean, but I've scaled things. So okay, so anything that I went over that you don't like, or that, well, there's probably a lot you don't like, or you have other questions? You can do those. Wow, okay, maybe you're just like, just get it out of here. So as I mentioned, please do let me know if you have complaints about your test, about the grading, about anything. Bear in mind that if you look online and if you're confused about what you see online, I can help. I can sit down next to you and say, hey, look, here's what it says, and that's your grade after the grade inflation. I think I put it in there as grade inflation. So, because technically that's what's happening. Grades are getting inflated like a balloon. Okay, let's see. Cooper will get his, and he can inflate his own grade. Okay, let me see. So I need to change gears, figure out what we're doing today. Okay, I don't want to do that. PowerPoint, probably. Yeah, there's Psalm 51. It's good. You can read it later. Well, good. Maybe I'll bring it on Friday. Oh, here's who I visited over there. This is my second grandson. Here, I'll just show that to you for fun. There. So out in Boston. So there he is. He's happy. 3 months old, weighs over 20 pounds already, which I know. If you know about babies, that's super unusual. Let's see. Where is the thing we're doing, though? Thought we had, oh, there it is, continuous random variables. Okay, there we go. Okay, we're moving on finally to continuous random variables. So a continuous random variable is something you're already familiar with, believe it or not, because you've all had statistics and you've done, oh, here, I'll show you what you've done. Just a minute. I think I've got this on here because I just taught statistics this morning. I don't want the introductory offer, no. Let me find, is it, where did I put it down here? No, that's something else. I don't know. I don't know where it went. Wait, let me just check one more place. I might have it here. So we just did, oh, here it is, central limit theorem. There, yeah, you're familiar with this. That look familiar? Or here, just a minute, I'll show you something that should be super familiar. Where is it? Oh, did I not? I did not save my ink, drat. Oh, well. Well, back in statistics, you might remember whoever it was who taught you statistics forcing you to make a normal curve and shade the normal curve. It was to help clue you in as to, at least for especially the non-math students, clue them in as to what the probability would be or the proportion would be. So you draw this nice normal curve, and then you shade, and then you have to use Excel or your calculator, depending on who taught you. Back in the olden days, we used to look these probabilities up in a table. In fact, with this class, I think there's a table in your book. We'll find out. That won't be until next week, I think, when we do the normal curve for real. But probabilities, you could find probabilities. It's an area. So an area, you know from calculus that an area is just an integral. And so if you're supposed to come up with an area under this normal curve, you could do it using an integral. You might say, well, why don't we make our statistics students just do an integral? Well, the reason is that some of them don't know calculus, and beyond that, this does not have an elementary function antiderivative. So that's the main reason. So let's skip that. We'll come back to normal curves, but I just wanted to point out that we do have this as sort of a prototype for continuous random variables. In general, a continuous random variable is a random variable that has a continuous probability function. Now, that I wouldn't write down. This is the technical definition, but I'll read it to you because all those letters have meanings or symbols. So suppose there exists a function that maps the reals onto the interval from 0 to 1, such that for every set of numbers or numbered pairs that are real numbers, the probability that x is in that set is an integral over the over that set for the function. Then that's continuous. So in plain English, the basic rule is you want a continuous random variable to have what's called a probability density function that is continuous and differentiable. So this here is a probability distribution function right there. So let me zoom back out so you can see it all, and then we will talk about what it means to be a probability distribution function. Because we kind of skipped over that. We may go back to it, but I thought it wasn't that useful, at least for most of it. It seems like probability distribution functions in general are kind of confusing until you have the idea of a continuous random variable. Okay, so here's what this is. You see this here? It says we want to know the probability that x is less than or equal to some number. And we want that to be a function. And we want that function to be both continuous and differentiable. If you have a function that, well, a probability situation that follows that rule, then you have a continuous probability distribution. Let's see if I can show you an example of this. Yeah, I don't want to hurt this. Just a minute. I don't mind hurting this though. Here's a pencil. I throw the pencil. It lands over there. it lands at some angle. The angle that it makes, which I could show you. We will do this so you can all see and enjoy, including Cooper from home. Okay, so I throw this over there. There it lands, and you can see that it makes an angle with the wall. Okay, so that angle, what would you say? That's about a 70-degree angle? I don't know. So if this is the horizontal here, 70 degrees. So it makes some angle between 0 and 90 degrees. We'll go in degrees. Well, it turns out that there is a probability function for that. And specifically, the function f of t is equal to t over 90. Okay, we'll explain why that is a little bit later. We have a name for this function, well, it's a linear function, isn't it? But if I want to know the probability that, that my angle is less than or equal to, say, 30 degrees, then that's going to be 30 over 90, which is 1/3. It kind of makes sense. If I throw my pencil over there again, oh, actually that is, it's actually almost exactly a 30 for Cooper. And for everyone who can't see my pencil. I'm not going to touch it. Put this back up there. Yeah, check it out. Yeah, that's pretty close to a 30-degree angle, isn't it? So anyway, oh yeah, here, let's go back here, just so we can see what's happening. So here's the thing: is it could land anywhere, and I'm measuring the angle, like that would be 30 degrees as well. So it could land any angle, and so any angle between here and here is less than 30, and then you go further up, you get more than 30. So anyway, whether you believe me or not that this is the right probability function, you could compute probabilities using that. That's the idea there behind a distribution function. I could do the same thing. I could say, what is the probability that I get between 45 and 60 degrees? I'll bet you could figure this out. Take a minute and see if you can figure out what the probability of being between 45 and 60 degrees is for this cheesy experiment of me throwing the pencil over there and looking out there to see why Kaler is taking photos. Oh, it's actually almost 0. It's like a 5-degree angle. It's really close to 0. So does anyone have any guesses as to what you think the probability is for being between 45 and 60? No one wants to guess? It's as obvious as, if you think it's obvious, yeah, it is. And if it's not obvious, then it's okay. Yeah, what do you think?
Would it just be 45 over 90 times 60 over 90?
Oh, almost. You got the right idea. Yeah, so that's the right idea. So you want to be between 45 and 60. So let's do it this way. The probability of being less than or equal to 60 is 60 over 90. And the probability of being less than or equal to 45 is 45 over 90. And then, I don't know if you remember this, but back when you were taking statistics, when you learned about Excel, at least when I teach statistics, I always talk about Excel as being leftist because all the functions, well, they're like this. They think of the probability to the left. And so do you remember what you did when you wanted to find the probability of something between two numbers? Yeah, you subtract, right? You take the top one and then subtract off the bottom one. So yeah, you do certainly do this and then you subtract. And then that'll give you between. So 60 90ths minus 45 90ths. They're going back there to take pictures. And they're going to make noise. Maybe they'll use their blender as... Oh, it was a blender. Yeah, remember, they were making salsa. So they were using that was what it was back there. That, remember a week or 2 weeks ago, about a week and a half ago. Anyway, I went and investigated. They offered me some, but I declined. It didn't look like the greatest salsa, let's just say. Okay, so let's see. We've got this. Very nice. So probability density functions have, oh, here, before we do this, here, let's do this. So the distribution function, wow, that's really bright on here. It's not bright up here. The distribution function, capital F of t, is the probability that you are less than or equal to t. The density function is the function that we're going to use most of the time to compute probabilities, even though probabilities are defined in terms of this. And the reason is that a density function, we can apply calculus to it to get the distribution function. So there's going to be this relationship we have between a density function and a distribution function. The integral of a density function, you'll get a better feel for what density function is in just a minute, but the integral of a density function is a distribution function, and if you have a distribution function, the derivative of a distribution function is a density function. So for example, the standard normal distribution that we're all familiar with is a density function. So this is a density function, that normal curve. And then when you compute an area, the areas, you're actually doing areas, so you're doing the antiderivative of that to get the distribution function. But this curve itself, that curve is called a density function. It's super confusing because we use these words that both begin with D, and so it's hard for me to, like I remember it being difficult for me to keep track of which was which. Distribution, that's the probability. Density is the thing you integrate to get the probability. So we'll practice this some. Okay, so some properties of density and distribution functions. So once you know you have a distribution function and a density function, so let's go through these one at a time. The probability, the cumulative probability that x is less than or equal to t is the integral from negative infinity to t of the density function. So there's the relationship. We just had that on the other slide. If you integrate a density function over the entire real line, you always get 1. Always. Now, this looks scary, I know. Negative infinity to positive infinity? I don't like that. Don't fret. You're not always going to have to go to infinity. We'll see why in a bit. For example, my angle thing, this stupid pencil angle thing that I'm doing, the angle is between 0 and 90 degrees. And so the density function only exists from 0 to 90 degrees. Anywhere else, the density function would be 0. So if you have a density function like that, you only have to integrate over the range of values that are applicable to this particular density function. So we've already had that. The derivative of the distribution function is the density function. If you want to know a probability, this was kind of hinted at with the normal curve, you just compute the integral of the density function. Because density functions are continuous, all 4 of these are the same. So it doesn't matter if you're less than or equal to or just less than. All the same. This is only with continuous distributions, which we aren't going to have any mixed distributions, but there are some distributions that are mixed in the sense that there's a bunch of probability at one point, and then it jumps so it's a discontinuity in your density function, which makes it not continuous. But yeah, that you don't have to worry about unless you end up going and taking the actuarial exam, in which case you'll worry about it. And then here the density function is always bigger than 0. Oh, same is true of the distribution function, but density function is as well. Okay, so what are you going to have to do with this? Well, here's an example. Let's see. Let's focus on this one right here, the second bullet point. So this second bullet point, so that the integral over the entire domain is 1. It's kind of like the sum of all the probabilities equals 1. So let's do that with this example. So we have, first of all, this is a probability density function, and notice the C there. So the C is just a placeholder. It's like, well, I don't know what that number is, but I know that this is proportional to x squared times e to the negative x. So let's figure out what c is. To figure out what c is, what we're going to do is we're going to integrate over the entire domain. Sorry, I just noticed that this only makes sense if x, here we go. I should append this. Here, I'm going to do it on Notability. That way I'll get it right. There's something missing. Let's see, I'll put it back here. Just a sec. So this is f of x is equal to, here's what's missing. C x squared e to the negative x if x is greater than or equal to 0, and 0 if x is less than 0. That's better. Otherwise, the problem is that e to the negative x blows up when you put negative numbers into it, and so the probability would, you'd never be able to find a value for c. Okay, so notice that the domain where this thing is defined is all of the x's bigger than or equal to 0. And so the way you're going to solve this is you do the integral. Well, okay, I will write it out the correct way, but then I'll write out what you're going to actually do. So this is the correct way to do it. Give me a sec here. Don't write this down. Well, I mean, you can if you want to. E to the negative x. There we go. Okay, so, and this is because when x is less than 0, you're using that function. And when x is bigger than 0, you're using this function. Okay, but honestly, if I were looking at this as a test problem or a quiz problem, I would not even write the thing that I've done lime green here. I would just immediately just go to this, because this is all 0. It's like the density function doesn't exist over there. So just go to the, cut to the second line here, and let's just do that. Okay, so let's do this antiderivative. This is going to be c times the integral from 0 to infinity of x squared e to the negative x dx. All right, anyone know what we're doing here with this antiderivative? Do you guys have a technique you want me to use? I'll do it. Can you name it? Well, what is it? Oh, yes. Integration by parts, one of our favorites, right? So let's do integration by parts. I'm going to use tables. Maybe you've learned about doing integration by parts by tables. If not, this will be fun. So in integration by parts, you let u, okay, so this is the integral of u dv is equal to uv minus the integral of v du. So you remember this from the olden days, Calc 2. Anyway, the way that you do it, you have to identify your u and your dv. So the way that I do it usually is I start off by doing this. I'll identify the u and the dv in a table. And in this case, I think it's just going to be like that. And then I repeatedly, because in this case, you're going to have to use integration by parts multiple times. So if you did this by integration by parts, you do integration by parts twice. And I don't want to have to do integration by parts twice because it's kind of a pain. So I'll use a table. So I do derivatives, 2x, 2, and 0. You do derivatives of your u and do antiderivatives of the dv. The antiderivative of e to the negative x is negative e to the negative x. And then that's e to the negative x, negative e to the negative x. So just to remind you, you might have seen this before. You're going to be doing derivatives, d over dx. Here you're going to be doing the integral with respect to x. Now we're almost done. To do the antiderivative, we're going to line these up on diagonals. There, there. Everything is a diagonal in math, isn't it? So there they are. That's going to be my integration by parts. And so my final answer is going to be the first diagonal. In just a minute. Make this look better. Oh, come on. There. Okay, so we have the first thing, which is negative e to the negative x. Negative x squared e to the negative x. So I've done x squared times negative e to the negative x. And then you subtract the next one. So this one you leave whatever sign it is. It happens to be negative. The next one you're going to subtract, and you get 2x e to the negative x. The next one you're going to add, which is going to be negative 2e to the negative x. And this is evaluated from 0 to infinity. Yeah, sorry, this one got a little scrunched up. So notice I'm just multiplying. This is just a shortcut to whenever I have to do integration by parts. And if I recognize that I'm going to have to do multiple integration by parts, this is just an easy way to do it. You just do derivatives till you get 0, do antiderivatives, the same number, and then just crank this in. It's just the same as doing that multiple times. And the reason for the plus, so here I'll do it, I'll put the plus, minus, plus. So you leave this whatever sign. The plus just means leave it whatever sign it is. Here you're going to negate this. Here you leave it whatever sign it is. So they all end up being negative. Now let's evaluate this from 0 to infinity. So let's see, what do we get? When we plug 0 into all of this, I get, infinity first. Oh, do you mind if I don't write limit as b approaches infinity? You probably don't mind. Yeah, technically I should put a b here and do limit as b approaches infinity if I want to be really correct. But I think we all can just think through like, okay, this limit, whatever. You got these e to the negative x's that are going to be zeros. So this ends up being 0 for the upper limit minus, I think it's just negative 2 for the lower limit. So the 0, this is what you get when you do, and this is the limit as x approaches infinity. Ends up being 0. You can double check. Technically, I should actually be doing L'Hopital's rule. It's going to be all right. Okay, but anyway, notice what I'm getting here. When I get done, I have just 2 times whatever c is. Let me zoom out just a bit so you can see where this is going. So this, all of this should equal 1. That should equal 1. This should equal 1. That should equal 1. So c must equal 1/2. So c equals 1/2. So if you're given a density function that doesn't have everything, like it's missing a term like a c here, you can figure out the c by doing the integral. Maybe integration by parts, maybe not. You got it there. 10 minutes. Okay, and then I can go check on what they've made back there. Maybe they'll share again. Okay, so that was part 1 of this problem. Let me go back. I need to see the problem. Find the distribution function. Okay. Well, the distribution function is the antiderivative of the density function. Okay, so the distribution function f of t is here. I'm going to write it like this. Move this over. So capital F of t is the probability that x is less than or equal to t. And because x can never be less than 0, because of this right here, we're going to do the limit, or we're going to go from 0 to t. So we'll go from 0 to t of c x squared e to the negative x dx. Okay, now we have to go through this rigmarole again, but we've already done this antiderivative, so I don't think that I need to do it again. In fact, it's right up here in this, right there. So if you don't mind, I'll just copy it down. E to the negative x times negative x squared minus 2x minus 2. I factored as well. And this is going to be from 0 to t. So that's just this. So little, so little. Yeah, I just took that antiderivative and rewrote it down here. I factored out the e to the negative x because I thought it would be easier. And then the c. The c is just right there. So everything's good. All right, almost done. So now we have to plug in our limits. And this is going to be, I think when you put a 0 in there, I get 1. Okay, well, do the upper limit first. E to the negative t times negative t squared minus 2t minus 2 minus negative 1/2 times 2. I think that's what you get. Yeah, because of this negative 2 times 1 times 1/2. So it'll end up being 1. So I guess I could write it like this. 1 minus 1/2 e to the negative t squared plus 2t plus 2. So just factor out the negative here so that it looks a little bit better. I don't know, it's maybe more than you need to. But that's the density function, or distribution function, sorry. So distribution function is that cumulative probability. All right, let's go see what else we got. So that, I think I've got a couple more examples that we can do. Let's see, this one's easier. This one's easier. Yeah, see if you can do this one yourself. Okay, so here is a density function, and you're supposed to come up with, first of all, the value of c. I'll show you the rest of it in a minute, but let's see if you can get c out of this thing. And notice that this density function is only defined between 0 and 2. So when you do your integral, you can ignore everything outside that interval. Just go from 0 to 2 for your integral. And I'll interrupt you a couple of times here to, so that we all are in the same place. Take me a minute to do attendance first. Probability. And take attendance. Cooper, come on. Let's get some random students. So let's just get it set up so that we're going to do an integral. So Rachel, what integral do you want me to write down? All right, very nice. And I put my c inside, same thing. I'll move it out, sorry. All right, so we've got that integral. So Briar, what is that? What should that equal? Yeah, very good. So this is the integral over the entire domain. See, everything else is 0. So this is the only place that matters. That should equal 1. Now we can do this. Let me clean it up. I'll do what Rachel suggested. And I'll put the c on the outside of the integral. Let's see, 8 minus x cubed. All right, now we just have to get this antiderivative. Audrey, you know the antiderivative, don't you?
8x minus 1/4 x equal.
Beautiful. I'm just going to write it like this, same thing. So I want that to equal 1, and we're going to evaluate this from 0 to 2. So go ahead and plug in your limits. So upper limit, lower limit. Zane, what did you get for your for the upper limit when you plug 2 into all of that? 12. Okay, 12, very good. And then we got to plug the lower limit in. Sydney, what did you get when you plugged the 0 into all that? Yeah, 0. I always like to make sure though, because I know it usually is 0, but
2 times 8. Yeah, but minus 4. Okay, I forgot to put
yeah, Zane did too much in his head. I've taught him to try to show off, right? Sorry about that, Zane. I'll try to pull it back. Okay, good. We got 12. Everyone else got 12. So let's get this. Let's finish it up, and then we'll get the second part of the question. Let's see, Chelsea. So what is c equal for this to work out? Yeah, 1/12. Very good. So 1/12 is what c is. Okay, so now we're going to do something with this probability density function. Oh, it's blocked. Let's fix this. I think you can all do that. Let me get rid of all this. We're going to compute the probability that x is bigger than 1. So c is 1/12. So now let's get the probability. This is also, because it's a probability, it's going to be an integral. Alyssa, what's the integral that you're going to use to represent this?
Integral of c times
8 minus x cubed dx. But what are the limits? Oh, interesting. Okay. You can go from 0 to 1 and then subtract from 1. Is that what you said? Yeah, that you can do that. I'm going to do it the easy way, though, or the easier way, I think, and go from 1 to 2, because bigger than 1 means everything from 1 to 2. But yes, you certainly could do the 1 minus. I know you love that. Some of you did that on your test when it actually created more work for you, which I respect. You know, you want to do more work, that's fine. But there we go. Okay, we've already done this antiderivative, and I erased it. But let me see if I can remember what it was. It was 8x minus x to the 4th over 4, evaluated from 1 to 2. Okay, so that's what we're going to have to do. So we have to plug in these numbers, upper limit, lower limit. Nolan, what do you get when you plug that 2 into that? 12. Oh, yeah, that's right. It's 12. And then we need to do the lower limit. You're not here, but you would know how to do it, I'm sure. Hannah, what do you get when you plug 1 into all of that? Yes, 7.75. You know what, I think 7.75, that's 7 3/4. Let's write that as 30/4? 31/4? Yeah, let's do that. And then 12 is 48/4. So let's see, 48/4 minus 31/4 is 17/4. Yeah, you could use a decimal. There's no problem with you using your calculator and having a decimal. I don't mind. But 17/4, so 17/48. Is that what that ends up being? All right, very exciting. Is there anything else here? Okay. Here's another one. This one has a decimal, so you might, we've got only 1 minute. Darn. Oh. Okay, so I don't know what is on the homework. Hopefully not that. Oh, but you could all do that because of this. Well, we'll deal with it. I guess I know there's something on the homework. I don't know if there's expected values, they're bad, but yeah, do what you can with the homework. And if there are expected values, you can skip those. I give you permission. So just do the ones where you're trying to compute C and you're computing probabilities. And come talk to me if you have problems with your exam after I turning off the recording right now.